1.5 independent events. Okay, in other words, replacement. So an independent event is when one event has no influence on the probability or chance of another event. Now, compound events is when multiple events in a probability experiment may or may not, and they may or may not affect one another. Okay, so example 1, consider a skills competition where each baseball player will attempt on catching a ball, where it is equally likely that the player catches the ball or misses the ball. So the tree diagram below shows all possible outcomes on 3 attempts. So catch and miss is going to be the first attempt. Catch, miss is going to be the second attempt. And another catch, miss on all of those are going to be the third attempt. So what we're going to do first is we'll go ahead and label all probabilities here. So these are 1/2 each. Okay. And if we think about the number of outcomes there are here, we go ahead and we count 1, 2, 3, 4, 5, 6, 7, 8. There are 8 outcomes. And likewise, 1/2 times 1/2 times 1/2 is going to be 1/8. So each of these events occurring is going to have a 1 out of 8 probability. Okay, so for B, state the total number of outcomes. So we already said that that's 8. C, what is the probability that all 3 balls will be caught? So this is a probability of a catch, catch, catch. Okay, or you can do 3 catches. So that only happens one way. It's catch, 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 and that is a 1 out of 8 probability. Now, let's talk about situations where we already know something has occurred. So D, if we know that the player has already caught 2 balls. So what that looks like is, okay, so catch here, catch here. So we already know that this happened and this happened. Now, what is the probability that they will catch the 3rd ball? So what we can visualize this as is we're going to actually start here. And then it's still a 50-50. So the probability, let's write this in blue. Okay, so the probability of a catch, and then I'm going to show you guys this vertical line means given. Okay, given that there's 2 catches already. So we're given this piece of information, so we're told that we start here. And at this point, there's a 50-50 chance. Okay, so E is asking, why is there a difference between the answer in C and the answer in D? Because both of these are technically asking the probability of 3 catches. The difference is that D gives us information. So D gives us information. Okay, this changes the probability. So which changes the probability of the first 2 catches to 100%, because they're saying this happened. So instead of that percentage being 50%, it's now saying like, no, 100% that happened. Now let's just assess that last catch. Okay. And you can say, like in C, all catches are unknown. It's an A. All catches are unknown. Okay. Let's talk about product rule for independent events. So when 2 events, A and B, are independent, the probability of both events occurring together is the product of their individual probabilities. So the probability of A and B happening is going to be the probability of A happening times the probability of B happening. Okay, this is where, when we did the probability tree diagrams and we started multiplying them, this is where I said, let's just keep that in the back of our minds. Now it's an actual formal theorem. So let's go to example 2. A game is played where a 4-sided die is rolled in a 3-section spinner with colors red, yellow, and green is spun. Okay, so I provided the tree diagram. It's disconnected. So the 1, 2, 3, and 4 are all the first roll of the die. Okay, so let's go ahead and label the probabilities. This is going to be a quarter, a quarter, a quarter, a quarter. Okay, so state the total number of outcomes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the total number is 12. We're going to label the probabilities of each event. So the probability of each of these sides being rolled is 1/4. But then we could have a spinner with only 3 sections equal, and it's 1/3. Okay, so this second part is 1/3 for each of these. Okay, so when we multiply 1/4 by 1/3, okay, if you think about 1/4 times 1/3, we get 1/12. And then logically, there are 12 different outcomes. So if these are equally likely, then the probability of each of these occurring is going to be 1 out of 12. Now, let's make a game using the 4-sided die and 3-section spinner. In the game above, do players 1 and 2 have the same probability of winning? And I'm going to loosely use the word fair game. Okay, so player 1 wins if an odd number is rolled and a red or green is spun. So probability that player 1 wins is going to be odd number and red or green. So odd number is 1 and red is here. Odd number is 1 and green is here. So that's 2 different outcomes. Or 3 in red and 3 in green. So I'm getting 4 out of the possible 12. Now the probability that player 2 wins is if a prime number is rolled and a yellow is spun. So 1 is not a prime number, 2 is. So 2 and yellow, so that's one situation. And then 3 in yellow is another situation, and that's it. So I get 2 options or 2 outcomes out of 12. And player 1 definitely has a greater probability of winning. And then the third bullet, it just says neither of the 2 outcomes occur, then there's no winner and they just play again. So no, this is not fair. Okay, player 1 and player 2 do not have the same probability of winning. Okay. Applying the product rule for independent events. Okay, we're going to go back to this multiplication. When driving to work, Marissa states that there's a 0.75 probability that she will wait for at least 1 red light. Okay, so the probability of a red light is 0.75. Okay, as the complement, the probability of not stopping for a red light would be 0.25. Okay, remember these have to add up to 100%. So you can just take, I call it like the flip, but it's the complement, or it's 1 minus 0.75. Now, keep reading, and there's a 0.6 probability that she'll hear her favorite song. So, probability of the favorite song is 0.6. So, probability of not the favorite song is 0.4. These are completely independent of one another. Okay, the probability of hearing a favorite song and stopping at a red light do not change based on each other. So, what is the probability that Marissa stops at a red light and I'm going to introduce this notation. I'm going to put this as it looks like a very, very smooth N. And this stands for and. That's how we read that. So red light and hearing her favorite song. So what we're going to do is we're going to multiply the probability of the red light times the probability that she hears her favorite song. So I get 0.75 times 0.6. And we just multiply that. I get 0.45. Okay. And what is the probability of Marissa not getting stopped at a red light? So red complement. Oh, I want to put these together for notation. And hearing her favorite song. So what we're going to do is we're going to do probability of red complement times probability of your favorite song. Okay, so red complement is 0.25 times probability of a favorite song is 0.6. I get 0.85. Let me try that again. 0.15. Did not look right. Looked too big. Okay. And I do want to just note, these two are not complements. Okay, so not complements. If you think about all four of like the subsets here, the four options are red light, favorite song. There's not red light, favorite song. There's red light, not favorite song. And there's not red light, not favorite song. So we've only taken into account two of these. So we have to do the other two in order to actually add them up and make sure that they add to 100%.